So if you are doing calculus with these things, right? Like this is a parametric curve, and I want to take like the derivative. I can denote the derivative with a little r prime, like we normally do. And taking derivatives is super, super easy. You just go element-wise, and you take the derivative of each thing. So I would write I cosine of t plus j minus, times negative sine of t. Or, like Stephen said, I could be writing this like minus j sine of t. And then lastly, I would have plus k 2t. You could write 2kt, it doesn't really matter. All the same, but this right here is the derivative. And so as long as you remember how to take derivatives from Calculus 1, these new kinds of derivatives that we're going to be taking for like parametric curves, or like I said, a parametric curve is the same thing as a vector valued function. So if you want to take the derivative of a vector valued function, then you just take the derivative of each component separately. Okay. What if you wanted to take the antiderivative? Well, since this is the derivative, then the antiderivative is also just as easy, right? So if you started from this r prime of t, and I ask you what's the antiderivative, that's just going in the reverse direction, right? And so to find the antiderivative of some vector valued function, again, you just find the antiderivative one component at a time, right? So maybe I could write something like capital R of t to represent my antiderivative of the blue. And so that would be I times what? It's the antiderivative of sine. Yeah, negative cosine t. Plus j times what? Sorry, I'm taking the antiderivative of this blue. Yeah, that's what I'm doing. Yeah, so antiderivative of cosine is sine, and then that should be kt squared, so the antiderivative of that last term is kt cube over 3. Yeah, perfect. So now you're already experts. You already know how to take the derivative and antiderivative of a vector valued function.
There is not a plus a vector constant, right?
You're right. You're absolutely correct. So every time you take an antiderivative, you can throw in a constant, right? Because the derivative of a constant is just 0. And so you're right. We could say plus some constant, we'll call it C1i, plus C2j, plus C3k, right? You can just add any constant vector to your antiderivative, because once you take the derivative of your antiderivative, the derivative of those constants just goes away. Good point. Good point. All right, so if you wanted to take the definite integral from some lower bound to some upper bound of this vector valued function, r of t, we call it the parametric curve r of t. What we're doing here is we're going to take the antiderivative evaluated at b minus the antiderivative evaluated at a. So in other words, since everything else works the same, the fundamental theorem of calculus also works the same. So if you ever see a definite integral in your homework, it works exactly like you would think it would work. There's no surprises. Okay, what else? We talked about this last semester with parametric curves, but it's worth saying again that a parametric curve R of t is smooth if R prime of t is continuous and not 0. So remember, R of t is like a vector, so whenever I say 0, I just mean it's not the 0 vector. So by 0, what I mean is as long as it's not equal to 0i plus 0j plus 0k. But we're asking the same question. The previous curve we looked at was smooth everywhere, because we couldn't find any value of t that simultaneously made both of the components 0. But now for this equation, we're asking for this vector valued function of this parametric curve, we're asking the same question: where is this curve not smooth? So, just like before, the first step is we have to find the derivative. So, I take r prime of t as equal to I, and this time my I component is going to be minus 3 sine t plus 3 sine 3t. My j component is going to be 3 cosine t minus 3 cosine 3t. So I'm going to set the I component equal to 0, negative 3 sine t, plus 3 sine 3t is equal to 0. My j component is 3 cosine t minus 3 cosine 3t equals 0. I could rewrite this system and write sine of 3t is equal to sine of t, and cosine of t is equal to cosine of 3t. All right, now, when is sine of 3t equal to sine of t? When is this satisfied? At t equals 0, right? Sine of 0 equals sine of 0. Cosine of 0 equals cosine of 0. And then we also said pi. We had the same system earlier. But sine of 3 pi is equal to sine of pi. Cosine of 3 pi is equal to cosine of pi. So there's at least 2 points. Huh?
We
Yeah, so let's graph it. Let's graph this now. So what I'm going to graph is my original r of t function. I'm not going to graph r prime of t. I'm just going to graph r of t. So that is something like 3 cosine of t, oops, and 3 sine of t. So here it is. Ta-da. Here's when t is equal to 0, it's right there. And then as t, my parameter, increases, I start to draw this little parametric curve. And then this is where we get to t equals pi. And there we go. That's what I've been waiting for. That's where my parametric curve is not smooth at t equals pi. And then also at t equals 2 pi, but t equals 2 pi is the same place as t equals 0, because this is a periodic curve here. It's a closed curve because I've got periodic functions. Okay. Anyways, this should be reminiscent because we actually taught the same lesson when we did Calculus 2 at the end of the year, right? When we were talking about parametric equations in Calculus 2. The curve is not smooth when, and very importantly, the derivative is equal to 0. All the components of the derivative are equal to 0 at the same time. Okay, so there are some properties that you should know that look pretty familiar to calculus students. Like, let's say I have 2 vector valued functions or 2 parametric curves. I'm going to call them R and U. So if you want to take the derivative of R of t dot U of t, so remember, R of t is going to be a vector valued function, so at any given parameter t, you can find out the components of R. And then likewise with u. So you can take the dot product of those two. If you take the derivative of this dot product, what you get is R of t dot u prime of t plus r prime of t dot u of t. That looks really, really similar to the product rule back in Calculus 1, only now we're talking about dot products and vector value functions. Okay. This one is also familiar and maybe surprising. But if you take the derivative of this, which is the cross product between these vector value functions, you also get this, where all of those are cross products. So again, looks just like the product rule, so that should be pretty easy to remember. Just remember that for parametric curves in 3D space, or for vector valued functions with 3 entries in the value of the function, that the product rule works with both the dot product of those and the cross product of these functions. The chain rule works just as before. So let's say that this w of t is just a scalar function, or you could call it a scalar valued function. In other words, this is like what we studied in like Calculus 1, where there's just like one input variable that we call t and there's one output variable that we call w. Then the chain rule works the same way. So just like you might suspect, if you take the derivative of r of w of t, then just like before in calculus 1, we're going to take the derivative of the outside function first, and then we multiply times the derivative of the inside function. But since w of t is a scalar valued function, that's not the dot product. That's just plain old normal multiplication, right? That's just a scalar times a vector. Maybe I should label that. That's a scalar, while this is a vector. So you just multiply all the entries in the vector times the scalar. And that's pretty much it. We've already talked about antiderivatives. We've already talked about definite integrals. We still have a little bit of time though, so let's do a few more examples. Like, let me give you this parametric curve. Okay. So there's a vector value function or a parametric curve in the IJK notation. What I want to do first is let's find r prime of t. So what is going to be my new I component of r prime of t? 3t squared. What is the j component of r prime of t? You say 4t? Okay. And then what is the k component? Three. Okay. The next thing I want to find is what is r double prime of t? What should my I component be? 6t. What should my j component be? 4? What is my k component? Yeah. 0. Let's find now r prime of t dot r double prime of t. So in my mind, I know I've said this before, but I really prefer the column vector notation. So in my mind, the way I'm thinking about it is like this. Just reminding you that it's the same thing. And the dot product goes that we multiply the corresponding entries in these vectors, and then we add up all of those products, right? So I would do 3t squared times 6t gives me 18t cubed, okay? And then 4t times 4 gives me 16t. And then 3 times 0 just gives me 0. So that is my dot product there. And the dot product should be a scalar, right? So if I plug in any value of t, that gives me a scalar, and that makes sense for the dot product. I forgot the dot product. Oh, sorry, the I where?
I and
Um, yeah, for the dot product, yeah, the product is a scalar when it's the dot product. If we did the cross product, then I would end up with a vector as my product. So let's do the cross product now. Okay. Now the cross product is going to be the determinant of this matrix right here, where in the second row I'm going to have 3t squared, 4t, and 3. And then the third row I get 6t, 4, and 0. And this cross product becomes I times what?
For the determinant of 43, 40, negative 12.
Yeah. Negative 12. Right. So whenever we are looking at the I component, we're looking at the determinant of this 2 by 2 submatrix. And this determinant would be 4t times 0 minus 4 times 3, which is negative 12. Okay. Minus j, don't forget the minus, because I always do, times the determinant of this 2 by 2 submatrix. That includes those and those. And so it's going to be negative j times what?
18t.
Negative 18t, yeah. So don't forget, the determinant is the upper left times bottom right minus bottom left times upper right. So minus 6t times 3. Okay, and then plus k times the determinant of this 2 by 2 submatrix. What is that determinant? Negative 12t squared, right? So it's 12t squared minus 24t squared, so that is minus 12t squared. And I could rewrite this like negative 12i plus 18tj minus 12t squared k, or in column vector notation, you could also write negative 12, 18t, negative 12t squared. Right? These are the same thing, either way you write it. Okay, any questions so far? I feel good about this. It's just easy derivatives, easy antiderivatives. In Calculus 2, we did a lot of really difficult antiderivatives. That was like a whole chapter in Calculus 2 is doing really hard antiderivatives. We're not going to do that as part of Calculus 3. That's not really the focus of this course, right? And so if I ask you an antiderivative problem, it's probably going to be like polynomials or sine and cosine. I'm not going to go off the deep end and be like, this vector has j component secant cube, so find the antiderivative of the vector. No, I'm not going to do that. So, yeah. So, no, I'll try to leave the antiderivatives really easy because that's not the point of Calculus 3. That was the point of Calculus 2, but in this class I'm just more concerned with you like sort of getting the geometry part of it. Let me look and see if there's any other things that might trip you up in these exercises.
Is that all of this section? 12.2? Is that all for 12.2? Like, theory-wise?
Yeah, that was all the new stuff. There's one thing that I want to say, and it might be like difficult for me to like really illustrate, but like if this is some parametric curve through space that we call like R of t, the sort of interpretation of any kind of point here is R prime of t. What am I trying to say? Whenever we talk about the derivative, the R prime of t derivative, the geometric interpretation of this is that it is a vector that is tangent to the parametric curve. Okay? So we say that R prime of t is a vector tangent to the parametric curve. So, like in Calculus 1, we were doing functions that were like y is just some function of x, right? And so we had the derivative dy dx, called f prime of x. And what we said in Calculus 1 is that given some function here, that the derivative was like the slope of the tangent line, right? So this tangent line has slope f prime of x. If instead of a tangent line, you wanted to get a tangent vector, all you would have to do to get the tangent vector is write for the x component 1, and then for the y component dy dx. Because this, whenever we talk about the slope of lines in algebra, we tell the students in algebra the slope of a line is just the rise over the run. Well, in this tangent vector, you can think of the rise as being the dy dx, and then the run, the change in the x direction, as just being 1, or like the unit, right? And so if I was going to give you just a regular plane curve where it's y as a function of x, and I ask you for a tangent vector, that's what you do, is you just set x equal to 1 and y equal the y component of the tangent vector equal to dy dx. And so that would give you a tangent vector for this. But to find the tangent vector of any curve, if it's in 3 dimensions, if it's in 4 dimensions, if it's in 5 dimensions or whatever, all you have to do is you have to take the derivative of every component of the parametric curve. And so that's what works. So if this were in 3D, for example, then my tangent vector here is going to be dx dt, dy dt, dz dt. So if you're like, I don't know, I'm trying to come up with a example. If you're like shooting a rocket, just shooting a rocket through space and it's like traveling through the atmosphere and it's changing directions or whatever, the parametric curve itself is like the path of the rocket as it travels through space, and the tangent vector is again just the direction that the rocket happens to be facing at a certain time t. It's hard to draw. It's hard for me to draw in 3 dimensions, but that's what it means.
Would the tangent line be the direction of acceleration of an object?
That's a good question. No.
Okay.
Well, so it depends. So if r of t is describing the position of an object at time t, then r prime of t would not be the acceleration. R prime of t would be the velocity. Yeah. And what would the acceleration be?
Second.
Yeah, r double prime of t would be the acceleration. So, if you wanted to find the acceleration vector, you just take the parametric curve that describes the position of the object over time, and you take the second derivative to find the acceleration vector.